Throughout time, living organisms have evolved to survive in a variety of environments. As human beings, we are all well aware of how environmental factors such as temperature, wind, and other atmospheric conditions shape our lives on a daily basis. At a given time and place, these physical properties are collectively referred to as the weather. Using long-term weather observations, scientists have been able to make generalizations about the climate at different locations. At its simplest, the Earth's climate is largely explained by the relationship between air, water, and the sun. However, spatial and temporal differences make these relationships complex and therefore are not always easy to interpret. Luckily, most variations in climate occur over repeatable lengths of time or cycles, with some variability. For instance, most of us are familiar with some of the small temporal cycles that occur on our planet. We all know that we might need a jacket in the evening, even on a summer night. Although elementary, this is an example of a diurnal cycle on our planet due to the presence or absence of the sun. Many other cycles exist at various timescales due to local and sometimes distant phenomena. Some of these cycles occur over periods much longer than the human weather records, making them impossible to detect. Fortunately, we can use geologic records to better understand past climate regimes. Information such as those stored in marine fossils can prove invaluable in our search for a better understanding of the Earth's natural climate patterns. These techniques are all the more important as our current global climate becomes exceedingly unpredictable. Today, we will explore one of these techniques, starting at the very beginning. Our journey begins at the surface of the sea off Peru, where tiny organisms dominate, called coccolithophores. Why, hello there, Carmen.
Why, hello!
Interesting weather we've been having.
Isn't it just? You know, I've been cooking up a storm lately with all this carbon dioxide for my favorite recipe, photosynthesis. My fellow coccolithophore buds and I have been getting our autotrophy on in style.
Ah, yes, so you're a phytoplankton then?
Yep, that's right. But we're not just any type of phytoplankton. We also know how to calcify. Check out my calcium carbonate platelets called coccoliths.
Wow, those are very striking.
Yeah, my buddies and I are currently in the process of forming a bloom. It's tricky business being a coccolithophore, and I don't mean to brag, but we're kind of a big deal. You know, carbon cycle-wise.
Oh, is that right?
Oh yeah, that's right. Did you know that in a bloom there can be 1,000 billion of us? With our sheer numbers, we have a real impact on carbon flux from the atmosphere to the seafloor. As we bloom, we remove carbon dioxide via photosynthesis and at the same time release CO2 back to the atmosphere via calcification. With our calcium carbonate consumer brethren, the foraminifera, we're responsible for the ocean's vertical gradient and seawater alkalinity. Collectively, we transport nearly 1.5 million tons of calcite per year to depth.
That's some heavy stuff. Is there anything you coccolithophores can't do?
Want to know something else that makes us special? When we grow our coccoliths, we form organic compounds called alkenones that vary in their configuration depending on the temperature at the surface of the sea.
Wow, Carmen, that's rad. What's that smell?
Oh no! There must be a copepod near! That's our dimethyl sulfide stranger danger signal!
Oh, it looks like it's getting stormy topside.
Oh no!
And just like that, Carmen has climbed aboard the fecal pellet express. Zooplankton, such as copepods, help to accelerate the transport of carbonates, like Carmen, to the seafloor for deposition into the fossil record. Without this aggregation of material, coccolithophores would not be nearly as abundant in marine sediments. However, carbon faced another enemy, the calcite compensation depth, or CCD. At the CCD, the mineral calcite is thermodynamically more likely to dissolve than to remain as a mineral. Fortunately for geological oceanographers, blooms and aggregations by consumption help to assure that at least some of these organisms make it to the seafloor. After a long journey through the water column, our fecal pellet has finally reached the seafloor. It's here that her carbonate test has the possibility of being covered with overlying sediment and thus preserved in the fossil record. Paleoceanographers have long been studying sediment cores to reconstruct past oceanographic and climatic conditions. Shipboard multicores are used to collect replicate sediment cores up to a depth of 1 meter into the sediment. Depending on deposition rates, the cores can contain a record of sediment from years to tens of thousands of years before present. Much can be learned from the deposition of marine organisms, especially those that are abundant, well preserved, and serve as indicators for some oceanographic property, such as temperature. Coccolithophores can be used as such indicators. They are globally abundant primary producers, which have distinct environmental conditions in which they thrive. After cores are collected, they can be sectioned at precise increments for use in dating and further assemblage analysis. As sections move further down the core, they were deposited further back in time and are thus older than sections toward the top of the core. However, without using radioisotopic dating, it's impossible to get absolute date estimates. After sections are made, part of the sediment can be visualized using scanning electron microscopy in order to better understand the biological communities in both the substrate and overlying water column. After sectioning, smears of sediment containing biogenic and lithogenic fragments can be visualized at high magnification using scanning electron microscopy. Using these techniques, organisms such as phytoplankton can be identified to high taxonomic resolution. Since different organisms thrive in different environmental conditions, the presence of certain species can be used to better understand changes in oceanographic conditions, such as upwelling events and changes in sea surface height.
Whoa, look at this totally preserved coccolithophore. Normally you only have the lith, but this is the whole organism.
Dude, Michelle, that's so cool. How do you think that happens?
I don't know. Maybe a copepod ate it and it came down in a fecal pellet.
By analyzing samples from discrete sections of the core, paleoecologists can observe transitions from one community to another. Let's take a look at a section from deeper in the core. Wow, look at these ones, Michelle. They don't look like the coccolithophores we saw in the other section. Are these different organisms?
They are, Diane. These are diatoms. They make their frustrals out of silicate, which is like glass.
Oh, so why do you think we see different organisms at different depths in the core?
Diatoms grow in nutrient-rich waters, so sections dominated by diatoms are indicative of periods of upwelling. The cycling we see between sections dominated by coccoliths or diatoms are recording changes in global ocean circulation off the coast of Peru.
If coccoliths are found in sediments, they can also be used to reconstruct past climate regimes through the degree of alkenone bond unsaturation determined through gas chromatography analysis. A strong correlation has been found between the degree of alkenone bond unsaturation and the temperature of seawater during formation. Using sedimentary records from marine phytoplankton, geological oceanographers are able to gain insights into Earth's past climate. Thanks to biological processes like Carmen's coccolith calcification and consumption and aggregation of phytoplankton into fecal pellets, records of the physical environment are preserved in the sedimentary record. Through subsequent ecological analysis of phytoplankton communities using scanning electron microscopy and chemical laboratory analysis of organic structures like alkenones, we can learn a lot about the past environmental conditions. If we hope to better understand our current and future climate, it is imperative that we understand our past. The oceans present a unique opportunity for reconstructing the past, as marine sediments can remain untouched for hundreds or thousands of years.